Safety pilot, we are go for takeoff. Taking off in 3, 2, 1.
Welcome to the Flight Readiness Review of Team UAS NMIMS.
Hi, my name is Prayas Gupta. I'm currently pursuing my bachelor's degree in computer science at NMIMS University. This is my third year in the team. I'm the team captain. I've been working on imaging system and image processing. I'll be working as the interoperability server in charge at the flight line.
Hi, I'm Mohit Kenya and I'm currently pursuing my bachelor's degree in mechatronics engineering. I'm a senior at NMIMS University and I have more than 4 years experience in unmanned systems. This is my third year in the team. I'm the autopilot and electronics in charge in the team and I'll be acting as the GCS operator on the flight line.
Hi, I'm Ajay Mehta and I'm currently pursuing my bachelor's degree in mechanical engineering at NMIMS University. I am a senior and this is my second year in the team. I have more than 2 year experience in UAS technologies. I am a part of mechanical sub-team and on the flight line I will be the UGV in charge.
Hi, my name is Aldrich Fonseca and I'm currently pursuing my bachelor's degree in computer science engineering from NMIMS University. I have 3 years experience in unmanned technologies and this is my second year in the team. I am in charge of the imaging system sub-team and on the flight line I'll be in charge of ODLC.
Hi, I'm Ashur Dhaka and I'm currently pursuing my bachelor degree in electronics and telecommunication at NMIMS University. This is my second year in the team. I'm the electronics sub-team lead and on the flight line I'll be in charge of pre-flight safety checks.
Hi, my name is Apurva Agarwal and I am currently pursuing my bachelor's degree in mechanical engineering at NMIMS University. This is my third year in the team. I am the mechanical sub-team lead and the safety pilot of the team.
I am Dhruv Mendiratha, pursuing my bachelor's degree in mechanical engineering in NMIMS University. I have 2 years of experience in unmanned aerial systems and I am in the mechanical sub-team. During the competition, I'll be acting as a spotter.
Hi, my name is Abhishek Khambata. I'm currently pursuing my bachelor's degree in mechanical engineering. I'm a senior at NMIMS University and this is my third year in the team. I'm a part of mechanical sub-team and on the flight line I'll be controlling UGV.
Black Pearl 2 is a multi-rotor with 6 legs and 6 landing gears. We are using the Tarot X6 frame which is customized as per our requirements. Complete frame is made up of carbon fiber, making it robust and durable, along with lightweight. It has 3 center plates placed vertically above one another with desired gaps between them. Avionics, battery, camera and the UGV are mounted on these plates. Its all-up weight is about 10.5 kg. It can travel at a maximum speed of 14 meters per second. Its modular design helps in easy transportation and less setup time. Mounts for pixar, spool and camera were 3D printed for better usability and dampening the vibrations. The electrical subsystem includes 3 independent power sources for 3 different systems. The primary battery is connected to a central power distribution board which distributes the power to the ESCs, battery eliminating circuits and a power brick. The secondary battery is connected to the other BECs which power the PoE adapter for Bullet M5 and the onboard computer Odroid XU4. The secondary battery is also connected to a relay mechanism which again supplies power to the DC motor used for winding and unwinding the ether of the UGV. There is another tertiary battery which is the power source of the UGV for the drive to location task. It also actuates the servo on the UGV to detach it from the tether when the UGV touches the ground. There are 3 communication links between the UAV and the ground station. The first one is a 900 MHz telemetry link to transmit the telemetry data from the UAV to the GCS. The second one is a 2.4 GHz transmitter receiver link for the safety pilot to control the UAV as and when required. The third one is the imaging system communication link in which the onboard computer Odroid XU4 sits at the center of the imaging system. It is powered by the secondary battery using a step-down battery eliminating circuitry. It is connected to the relay circuit of the airdrop mechanism via the GPIO pins. For geotagging, the team decided to offload the imaging system from the PIXOC 2 autopilot. For that, the onboard computer is connected to an independent GPS module. The Odroid XU4 triggers the camera to click images at an interval of 1 second. The Bullet M5 connected to the Odroid is responsible for sending the images to the ground imaging system. This independence provides the team with the option of performing tasks at our own discretion. The onboard computer is running an open source API which is used for capturing images and transferring them to the GCS. The task of capture and transfer of pictures is accomplished by a script running natively on the onboard computer. For autonomous flight, the team is using the Mission Planner software as a ground control software running on the GCS. We have utilized the Autopilot hexacopter firmware running on the PIXOC 2 flight controller. For obstacle avoidance, the team has developed a code based on RRT Smart algorithm, which takes obstacle file as well as the waypoint file as an input and produces a new waypoint file with obstacles being avoided. For object detection task, the onboard computer, Odroid XU4, is running a script which triggers our camera Sony Alpha 5100 to click the images at a frequency of 1 Hz, and these images are stored in the flash memory of the camera. Odroid XU4 is also interfaced with an independent GPS sensor Neo 6M to tag the images with their latitude and the longitude. These images are fetched by the ground imaging system, where it will be received by a standard distributed system running a custom code which allows us to autonomously crop out the region of interest in the image. After the object is cropped, the JSON file is created manually, which is sent along with the cropped image to the interop server. Another software component of our system is the air delivery script preloaded on the onboard computer, which is used to wind and unwind the theta for air delivery task with its system. Team designed an unmanned ground vehicle for achieving this year's air delivery task. UGV comprises of the main chassis, where all the avionics are mounted, and payload plate, where the payload is safely secured. It uses PICSOC1 as its microcontroller. The UGV is programmed to drive autonomously to its desired location upon landing. This year, we are confident of attempting all the mission tasks. On our 10th practice flight this year, Black People crashed and suffered severe damages. After going through the log files, the team inferred that there was an issue with the battery, as it was unable to create enough potential difference across the motors. Since then, the team conducted extensive testing for the development of Black P42 system. Many types of testing techniques were used in a bottom-up approach. First, we implemented ground testing, which included unit testing, software level testing, and simulation testing. In unit tests, we conducted system tests like imaging system, unmanned ground vehicle, air delivery mechanism, T-ring cable strength tests, and anchoring tests to ensure that each system is foolproof and optimized before being airborne. All the codes developed by the team were first rigorously tested on the ground with various test cases and then implemented on the Black P42 system. After completing unit and software tests, we performed simulation tests using software in the loop technique, in which we also implemented our obstacle avoidance algorithm. Team also performed structural tests of Black P42 frame to check for the ability of the frame to take on increased payload. Once all the ground tests were completed, we finally integrated the system for manual as well as autonomous flights. The Black P42 system was additionally tested with an increased payload of 2.5 kg to ensure that it can comfortably accomplish this year's mission tasks. Before going for the autonomous flights, the team conducted simulation tests using software in the loop technique. Thereafter, the Black P42 system was auto-tuned to tune our PID values for safe and stable flight. Once auto-tuned, the team decided to conduct extensive manual tuning of roll, pitch, and yaw through brisk in-flight maneuvers for improved stability. The team conducted numerous flights both in autonomous mode and manual modes. The safety pilot got highly acquainted with maneuverability of the system during the manual test flights. Since the Black P42 system is highly tuned for stable flights and sharp maneuvers, it provides us with 93% waypoint accuracy. The team collected data from other competition performances and noted that about 1300 waypoints were attempted in total, out of which 1210 waypoints were captured. The team optimized the waypoint capturing ability by changing different parameters such as speed and waypoint radius. The team concluded that maximum accuracy was achieved when the system flew at 9 meters per second with a waypoint radius of 5 meters. For static obstacle avoidance, the team first implemented a simple tangent algorithm which created a new waypoint on the intersecting point of the two tangents from the circle. This algorithm gave us an accuracy of 70%. Then the team switched to RRT Smart algorithm, which now gives us an accuracy of 95%. Obstacle avoidance performance was first tested on 18 flights on over 71 obstacles, out of which 68 static obstacles were avoided. After comprehensive testing, the team has decided to continue with the Sony Alpha 5100 as it can successfully accomplish team's objectives. After comprehensive testing, it was tested against Nikon D3300, but Sony Alpha proved to be a better option in terms of weight, volume, and light sensitivity. The camera is able to click pictures at a resolution of 24 megapixels. At an altitude of 150 feet, the camera is able to take a pixel density of 10 pixels per feet. Upon calculation, we found out that the image clicked from the camera at an altitude of 150 feet can cover an area of 55.23 meters into 46.33 meters of the ground. The search area at the competition is about 3 lakh meters square. Hence, we are confident that we can comfortably cover the whole area even if we clicked one image per second. For the detection and classification task, the team developed a code which first detects the edges from the image. These edges are of the alphabet to be recognized. Formally, edge detection embodies mathematical methods to find points in an image where the brightness of pixel intensities changes indistinctly. The first thing we did is to find the gradient of the grayscale image, allowing us to find edge-like regions in the X and Y direction. We then applied canny edge detection, a multi-stage process of noise reduction, finding the gradient of the image, non-maximum suppression, and hysteresis thresholding. This code was first trained using standard computer-generated graphical alphabets. About 100 different samples were used, and the code gave us an accuracy of about 95%. Then the code was tested on actual objects captured from Black People 2 system. Once the code was fully functional, it became easy for the team members to manually classify the attributes of the objects and fill them in the JSON file format. As mentioned, localization task. The team has offloaded the job from Pixoc and it is being done through another GPS module, Neo6M, which is connected to Odroid XU4. Neo6M module geotags each image and writes the latitude and longitude of each image in a JSON file with the same name as that of the image. This reduces the time to perform the task and increases our efficiency. The localization system was tested on 14 objects over numerous flights and gave us a maximum error of 27 feet from the actual location of the object and an average error of 12 feet.
Airdrop performance. A new air delivery system was designed for achieving this year's task. A tether mechanism using a high-tension cable was adopted for serving the purpose. The strength of the high-tension cable was measured experimentally. The high-tension cable has a factor of safety of 8. High FOS assured high G-shock sustaining capacity which avoided the UGV from detaching in windy conditions. The team checked the system's performance by testing it from our college building. The system was held manually and a dummy payload was allowed to descend. After performing the ground test, the delivery system was mounted on Black People 2. The air delivery performance was checked by performing various test flights. Team conducted total 7 flights for testing air delivery system, out of which 5 times the UGV landed within a radius of 5 feet. The inaccuracies in drop were due to incorrect CG. The incorrect CG caused to and fro motion which was then rectified. This year's delivery task required an UGV to be dropped with a payload which would then drive autonomously to desired location. After a lot of design iterations, the team came up with a design which was compact in size and well under the weight limit. Both the chassis and the payload plate are made up of sheet metal. Sheet metal provided the required strength with optimal flexibility. Due to low brittleness, the UGV didn't fracture easily. The UGV was finely tuned so that it didn't get deviated from its prescribed path. The team follows an airdrop protocol. The GCS operator gives a go signal to the safety pilot when loiter starts. The safety pilot actuates the primary servo which detaches the UGV from the payload plate of Black People 2. Upon actuation, the GCS operator runs the air delivery script. Then the UGV starts descending. Upon touchdown, safety spotter gives the go signal to the UGV controller. The UGV controller actuates the secondary servo which detaches the UGV from the high tension cable. The GCS operator runs the air delivery script again to wind back the high tension cable. After completion of winding procedure, Black People 2 continues its mission further. The drop tests of UGV were performed both in lab and test flights. Out of 7 mission tests, UGV completed 6 missions successfully. Full mission testing. After rigorous development, the team conducted various mission test flights. Performance of the integrated system for the mission was checked during these flights. Team members did their respective role during these flights which made them better. The team secured an average result of 83% from 9 test flights. After performing these mission test flights, the team is confident to perform exceptionally well in this year's competition. The team is ready for 17th AUVSI SUAS competition.